So my name, as I said, my name is Sid Parmeshwaran, and I'm an associate professor in the Rudolph Firel Center for Theoretical Physics, and I'm the host for today's colloquium, which is obviously hosted via Zoom. I'm very glad that everyone here has been able to join us for what is, I think, a recent record in colloquium attendance, and I trust that everyone is safe wherever in the world you are. Before I begin, here are some announcements and ground rules that were pasted into the chat already that will help make this a smooth experience. So first of all, we are hoping to record this meeting in order to reach as many people as possible. And so the recording may be released, possibly after some light editing, via either the department website or other platforms such as YouTube. For that reason, we'd like to make sure that everyone in the audience is muted when they are not speaking or answering a question or asking a question, and that they keep their video off for the duration of the talk. If you have a question, please use the raise hand feature in Zoom, which is usually in the participants menu, or type a message in the chat window. Several of us are monitoring that window and the participants window, and we will call on you whenever it's possible to do so. If you're called on and ask a question verbally, it will be recorded, and our assumption is that you're giving us consent to record you and for the recording to be distributed as mentioned earlier. If you do raise your hand, please do remember to lower it afterwards. If for no other reason, then it will let us know if you have another question. Okay, with those basic rules in place, let me introduce you to the speaker, Professor Victor Yakovenko. So Professor Yakovenko, who is the other person you can see on your screen, is a theoretical condensed matter physicist on the faculty of the University of Maryland at College Park in the United States. He's also a fellow at the Joint Quantum Institute at the US National Institutes of Standards and Technology. Professor Yakovenko was educated in the former Soviet Union, where he worked with Sergei Brzozowski for his master's degree and with the late Lev Petrovich Gorkov at the Landau Institute for his doctoral thesis, which he received in 1987. He then spent some years as a research scientist with Igor Zyaloshinsky, thereby gathering two of the authors of perhaps the most famous many-body theory textbook as his mentors. And then he diffused westwards to Rutgers University with brief stops in Orsay, Torino, and the other place that is not far from here. After 2 years at Rutgers, he joined the faculty at Maryland in 1993, where he's now a full professor. As I mentioned earlier, Professor Yakovenko is by training a condensed matter theorist who has done influential work on organic superconductors, quasi-one-dimensional systems, high-temperature superconductivity, and more recently on topological systems. His work on the complex systems of condensed matter has received many honors, including Packard and Sloan fellowships, and election to a fellowship in the American Physics Society. However, the topic of this colloquium, as you might have gathered, is about a very different type of complex system, namely money. For the past several years, Professor Yakovenko has delved into the field of econophysics, applying the ideas of statistical physics to thinking quantitatively about questions around the modern economy. His work has studied diverse topics, including the links between stock prices and turbulence, issues of the unequal global distribution of energy consumption, and today's topic, the pressing concern of economic inequality, made only more pressing in light of current events. With that introduction, and without further ado, let me turn you over to Professor Yakovenko.
Okay, thank you very much for the opportunity to give, my understanding is the first online colloquium at Oxford University so far. I'm very glad to do that. There are quite many participants, and I see some names that I know. Okay, so let's get to the top. So the title is, oops, just a second. The title is Economic Inequality from a Statistical Physics Point of View. So this is the kind of well, my plan for today is to give a kind of brief overview of the work that I have been doing here for about 20 years. So my first paper on the subject was published in year 2000, that's 20 years ago. And the title of this paper was Statistical Mechanics of Money. And since then, I thought I would just write this paper and we'll be done with that. But then somehow there was follow-up papers and follow-up papers. There were many follow-up papers here. And I still continue doing this. Most recent papers published in 2000, this year and previous year. And there were many collaborators over this time. So the outline of the talk is the following. I will have limited time, so I probably will not be able to cover all of the topics. So the topics that I do plan to cover is I will plan to start with statistical mechanics of money, just to introduce the whole idea. I will probably not have time to discuss debts, so I'll probably skip this. And then I will switch to the second part, which is very important, is showing you actual data on income distribution. And analyze it in the view of the previous or the first part of the talk. And just bear with me, somewhere toward the end of the talk, I do plan to show income distribution in the UK. I mean, I will show a lot of data for the United States, but I will also show some data for the United Kingdom as well toward the end of the talk. Now, I will probably not have time to discuss last topic about global inequality as measured by energy consumption and carbon emissions, but okay, so we'll see. Okay, so let me start. A little bit on the historical note, because it's a colloquium. So I'll show you two kind of portraits. First is Ludwig Boltzmann. And of course, all physicists know this is one of the founders of statistical physics. And in statistical physics, I mean, I suppose there is a little bit of a mix of the audience. I mean, most people from physics department, but some people maybe not from physics. So I will mention a little bit, you know, some few things for non-physicists just very briefly. So in statistical physics, the kind of basically the fundamental law of statistical physics is something called Boltzmann-Gibbs probability distribution, which basically says that the probability to have energy epsilon is exponentially decreasing function of energy epsilon. So I will discuss this in much more detail later. So anyway, for the purpose of this slide, I will associate the exponential function, exponential distribution, with the name of Boltzmann, okay? As inspired by statistical physics. And then another portrait, Wilfredo Pareto. Economists know this name very well. Physicists also may or may not know. He was educated at Politecnico di Torino. So he was originally engineer by education, but then he became a very famous economist. And one of the things that he did at the late 19th century, he actually looked at the data on income and wealth distribution. And he concluded, by doing data analysis, he concluded that it follows a power law. So again, for the purpose of this talk, the power law function will be associated with the name of Pareto. Okay, and these two simplest mathematical functions, exponential and power law, will appear recurrently in the talk. So it'll be kind of central part of the talk. So after this historical introduction, let me start with basically with the analogy where the whole thing started. Is some sort of analogy between, where the analogy between statistical physics and economics. So let me show you half a slide, kind of brief summary of statistical physics. Those of you who have taken those courses, of course, know all this. Those who didn't, that will be half a slide summary, especially for non-physicists. So let us consider a big ensemble of objects, like say molecules, basically like say air in this room. There are molecules floating around. And those molecules collide once in a while. And so let's consider a collision process between molecules or atoms. So, so one molecule comes with energy epsilon 1, another one comes with energy epsilon 2. As they collide, some amount of energy delta epsilon is transferred from one molecule to another one, and then they fly away with new energies. So there is redistribution of energy in collisions. This is like billiard ball collisions. But of course, as you understand, the total energy, the sum of the energies before and after collision is the same. So there is a conservation of energy in this process. And now the question is, if you have two billiard balls, that will be mechanics. But if you have zillions of molecules, that become statistical mechanics. So the question asked in statistical mechanics, if you wait for long enough time, let system come to some sort of equilibrium. The question is, what is the probability distribution P of energy epsilon in this kind of steady state equilibrium? And there are many ways to derive it. That's what we teach in courses for statistical physics. There are several different kind of derivations. They all give the same result. So let me very briefly show one derivation, but I don't want to do any justice to this. So this derivation is from the principle of so-called detailed balance. So let's consider the rate of transitions from the initial configuration to final configuration. So the number of transitions per unit time will be proportional to the probability of making transition and occupation numbers of these two initial states, right? Okay. At the same time, transitions are possible in the opposite direction. So this could be the initial configuration, and transitions can happen in the opposite direction. So the rate of reverse transitions is proportional again to probability of making transition and now occupation numbers of those which we call final states. Now in equilibrium, the two processes kind of balance each other. So these rates must be equal. And very importantly, in physics, there is time reversal symmetry. So because of that, the probability of making transition is exactly the same. So it be canceled out. And now the punchline, we have two equations, which can be summarized like this. Energy is additive, probability is multiplicative. And the only solution of these two equations is exponential function. Okay, so end of derivation. Okay, so that's one way to derive this Boltzmann-Gibbs distribution. And of course, because energy is dimensional, it has some units, we need to put some coefficient, which we call temperature, which is basically which has dimensionality of energy, basically is the average energy per degree of freedom per molecule or something like this. Okay, so anyway, so that's one way to derive it. Another way is by maximization of entropy. So you have a box where there is some gas, and there are many molecules that have some total amount of energy, but box is isolated. So this energy is partitioned, divided between the molecules. And it turns out the way it is actually partitioned is in such a way as to maximize entropy of that distribution, subject to constraint on total energy in the box. I will discuss this a little bit more on the next slide. So anyway, that's it. That's half a slide I wanted to say about physics. Now I want to switch to, well, economics. And so I often say that, too bad I cannot see your faces, but anyway, I often say that I made only two contributions to this field. One I will mention now, another one later. So one contribution, I changed the label. So watch this, energy, let's call it now money, okay? So that's it, that's one. So now let's consider a big ensemble of economic agents, not molecular, economic agents. And those agents, they engage into some transactions, meaning monetary transactions. So very importantly, I consider monetary economics, where we pay money in every transaction. So let's consider interaction between two agents. They have money balances, M1 and M2. So let's consider me and Sid. Okay, so he has some money balance, I have some money balance. He has money balance M1, I have money balance M2. And suppose I want to buy a glass of water or bottle of water from him. Okay, so I give him £1, okay, and he gives me the bottle of water. So this is transaction, right? So as a result of this transaction, his money balance is £1 up, and my money balance is £1 down. Now he gives me water in exchange. I drink this water, water disappears. Okay, we'll never see each other again. I never get invited to give this colloquium. So water, there's no more water. And then we never see each other again. We fly away. But his money balance is $1 up. Oh, dollar, pound. Okay, whatever. 1 unit up. My money balance is 1 unit down. So this transfer of money in transaction is a little bit similar to transfer of energy in collision between molecules. Okay, so but as you can see, there is a local, naturally, there is a local conservation law of money, right? We ordinary people like me and Sid and most people in the audience, we can only get money and give money. And so we just move money around. And now there is a question. Suppose we have a big ensemble, millions of people, very big ensemble. And so people engage in all kinds of transactions. And then the question is, in some sort of equilibrium, some sort of statistical equilibrium, what would be the probability distribution of money in this system? That's a kind of fair question to ask. And by analogy with physics, I made a conjecture that, well, I can argue that it might be probability distribution of money might be given by exponentially decreasing function of money, Boltzmann-Gibbs distribution. And because money have units, pounds, dollars, whatever, there must be some coefficient T, which I call money temperature, which is basically average amount of money per agent in the system. So that was the original conjecture. And let me show you some computer simulation that's just to illustrate this point better. So it is what is called these days agent-based simulation, which is a little bit like molecular dynamics simulation in physics. So we have a big number of agents, and we prepare a system in the initial state where we give every agent, say, 10 units of money. So we prepare a system in such that, in the state of perfect equality. Initially, everybody has exactly 10 units of money, exactly the same, equal. And so the histogram, the probability distribution, is a delta function. So this delta function represents perfect equality as the initial condition for the system. And then we start running a simulation. And the way we do this is this. I pick a pair of agents randomly, and then I transfer 1 unit of money. So just to keep it simple, of course, we did other rules as well, but the simplest one, just for illustration, transfer 1 unit of money. And then pick another pair of agents, transfer a unit of money, and so on. Just keep doing this. And the question now is, what happens to the probability distribution as we start running simulation? So let me start it. Okay, now I stopped it. So as you see, the probability distribution immediately broadens. So we get some kind of Gaussian shape, which is very typical for diffusion. So just because of just random transactions, some agents end up with higher money balance, and some agents end up with lower money balance. Now, the first moment of the probability distribution, like center of mass, if you like, stays constant because it's a closed system. So it has fixed number of agents and fixed amount of money. But the second moment, the width of the distribution, it increases, as it happens in any diffusion. So any diffusion process, you know, the variance, the second moment keeps increasing. So it's this diffusion based in money space. And so first important message here is the state of equality, let's say perfect equality, is totally unstable. You can prepare system in this delta function state, but once you start doing any transaction, just by the law of probabilities, some sort of inequality will immediately develop. Okay, so that's just this basically is just a property of random processes. But let me continue now running the simulation. So what happens if I continue running it? Now I keep running it, and then now we see it becomes asymmetric. So let me stop it. It becomes asymmetric. Why? Because of the boundary condition at 0. I did not mention it, but I do have the boundary condition in the simulation. Basically, I do not allow anybody's balance to go below 0, which is implemented like this. If an agent spent all of the money, so an agent has 0 balance, this agent cannot buy anything. Even if I wanted to buy a bottle of water, I cannot do this, I have no money. So if agents that picked up in simulation has no money, then we skip transaction, go to next agent. So in this way, nobody can go below 0, but people at 0 can get money. They, just a second, let me do one thing. Okay, yes, so they may work for somebody and receive money, so they may get paid. Okay, so in this way, there is basic impenetrable boundary condition at 0, so probability distribution is bounded on this side. And this is very similar in physics to ground state energy, right? For example, molecules in the air, their kinetic energy is necessarily positive. It cannot, it cannot be negative. Okay, so state with when molecules do not move, that's a 0 kinetic energy. That's the lowest energy state. We call it ground state. So most systems in physics, they do have ground state. There is limit on the lowest possible energy, but usually there is no limit on the highest possible energy. Of course, there are some special things like black holes, a gravitational system, which do not have actually can be negative, but that's
Victor. I think
yes?
Victor. I think there's a question.
Is it on chat or somebody want to ask or what?
So I think Armin Reichold has a question. I'll ask him to unmute himself and ask it directly.
Okay, go ahead. Yes, please.
Yes. Hi, Victor. Thanks very much. I had a question which asked, why do you think money is conserved? Because we have lots of interactions in which we take out a loan and then money comes out of nowhere. And also, you're missing the time reversal symmetry that we had in physics, that an interaction between two unequal, agents in this case should not necessarily have the other way, go the other way around. So these two assumptions, why do you think they hold?
Yes. All right. So first of all, let me address the second question. You're absolutely right. So I refer to time reversal symmetry, and roughly speaking, I can divide models. We don't really know what is the economic dynamics, but I can make I would say that this exponential distribution is kind of semi-universal, meaning if a model, whatever the model is, if it does have time reversal symmetry, then it is sufficient condition, it will have exponential. If it does not have time reversal symmetry, it could have something else. So this statement about the hypothesis about exponential distribution is not fully universal, because there is no reason, there is no fundamental reason for time reversal symmetry in economics, okay? However, of course, in a certain class of models, there may be. For example, in this particular model, $1 transfer this model actually does have time reversal symmetry, because I can give $1, I can get $1. So this particular model does have time reversal symmetry, and so a certain class of model does. A typical example of a model that does not have time reversal symmetry is multiplicative model. If I gain 5% and I lose 5%, I do not get back to the same, to the original value, the original balance. Mm-hmm. So as we proceed further down the talk, in fact, we'll have both kind of situations. We'll both have situations which are, you know, okay, so we'll encounter both examples. So it's not an absolute rule, but we'll see both examples.
What about the conservation of money?
Conservation, right. You mentioned loan. Loan means debt, right. And debt is an item. So, okay, so let me do this. Let me finish. Okay, so I started. I do it step by step. I start with the simplest possible model where debt is not permitted. Okay, that's what I'm showing you. Okay. And now once we finish discussion of this part, let's discuss very briefly what happens when debt is permitted, how results get modified. Okay. Right. Okay. So in this limited, narrowly defined model, okay, let me continue running simulation. And if I run it long enough, eventually, okay, now there may be some problems with video. Yeah, video does not go very well on Zoom because of frame rate, etc. Okay. I think it's kind of frozen on your screens, right? It doesn't move. Okay, you know, let me not try to run
Victor,
it further.
If you stop sharing and restart sharing, it will come back.
Yeah, I understand. But yeah, yes. Actually, let me go to previous slide. Okay, let me restart it. Okay, now I think it's running. Okay, it's running, and if you wait for long enough time, the distribution will come to the red line. Will stabilize at the red line, and red line is a graph of exponential distribution. So in other words, after long enough time, the probability distribution will stabilize at the exponential function, and then it will not change anymore. So that's what we expect in physics. In fact, I use this illustration when I teach statistical physics, you see, because it's easier to explain it using money. It's easier to explain statistical physics using this money as a system. Okay, so anyway, let's say we waited long enough, and now the distribution is pretty much exponential, and transactions continue, money keep moving, changing hands, but histogram doesn't change anymore. And what is special about this exponential distribution in particular is it corresponds to maximal entropy. What the graph at the bottom, it shows entropy as a function of time. So just one word for those who, for those non-physicists, entropy is a logarithm by definition, is a logarithm of multiplicity, and multiplicity is a number of combinatorial ways to produce this histogram. So the initial distribution, the equality distribution, right? There is only, multiplicity is 1, because there is only one way to produce this configuration where everybody has 10 units of money, right? And so logarithm of 1 is 0, so the initial state of equality had 0 entropy. And then as we run simulation, system spontaneously evolves toward the state of a higher entropy. That's the second law of thermodynamics. System spontaneously evolve toward a state of high entropy. And the exponential distribution is the one that was proved mathematically by Boltzmann, is the one that actually has maximal entropy. And so system saturates at the state of maximal entropy because it has the highest multiplicity, the highest number of combinatorial ways to, for example, I can have $10 and Sid had $20. That's one possible micro realization. Or it could be the other way around, right? So I have 20, he has 10. The same histogram, but different microscopic realization. And one can do combinatorics and show the exponential has a maximal multiplicity subject to constraint. Okay, so now, just one word couple words I want to say, and then switch to that. So I would call this kind of exponential distribution from physics point of view, statistical physics of view, I would call it natural inequality. Natural meaning that it's inequality that simply develops in the system. Inequality means that there are few people with high money balance, like few rich people, and many people with low money balance, and many poor people. And that's at least qualitatively sounds like that what it is in real life. And so in this case, in this model, it develops for purely probabilistic reasons. It's just theory of probabilities. And it develops also by, and the consequence of that is maximization of entropy. So now just a couple of remarks. First of all, I would argue that this model represents some kind of highly stylized, of course, highly stylized model of free market. Free market in the sense that anybody can interact with anybody, meaning everybody has equal probability to interact with anybody. Right? Of course, there's no structure in the model. Of course, this is highly simplistic. In reality, more complicated, but it's just a stylized model. And second thing is an equal opportunity society, because every agent has equal probability to be picked up for any transaction. So there is no like bias, discrimination, there is no abilities, skills, education, etc. So all these agents, they have no attributes in this model. In that sense, they have no personal attributes. And yet, highly unequal distribution develops in the system the same way as for molecules in the air. Okay, so of course this is like lottery. So in lottery, everybody has equal probability to win, but it doesn't. In other words, equality of opportunities does not mean equality of outcomes. Okay, that's all I wanted to say about this graph. But let me now say a couple of words about debt. Okay, so suppose now, yes, we allow people to borrow money. So suppose I reached zero balance, I have no money, but I still want to, I still want to get a bottle of water. So then I go to a bank and borrow money. Okay, and the act of borrowing, again, from physics perspective, it's like particle antiparticle creation. So you create actually a pair. So let's say I borrowed $100. So I get $100 cash, that's a positive balance, but I also have $100 debt, right? So my net worth is still zero after the act of borrowing. So if you take into account both positive, part, the cash, and negative part, the debt, the sum is still the same. So the act of borrowing does not violate that generalized conservation law if you count debt, but what it does, it relaxes boundary condition. Because now I can spend this cash, I can buy whatever food or whatever I want, this cash goes to somebody else in the system, but debt stays with me, right? So my balance now becomes negative. So now my balance becomes negative. So by permitting debt, we relax boundary condition and allow negative balances. That's basically what it does. It relaxes boundary condition. Another question is, let's discuss very briefly what would happen once we relax this boundary condition. Suppose we put no limitation on debt whatsoever. I mean, we need money, borrow. More money, borrow. Even more, borrow, not a problem. If you impose no limitation on debt whatsoever, you understand what can happen in this simulation. I don't have a simulation, but it's easy to imagine. You start with delta function, then you start spreading in both directions in a Gaussian manner, and if you keep spreading and spreading and spreading, it will never stabilize. If there is no boundary on debt, debt will go to minus infinity, and positive also go, go like this. And that, by the way, answer to another frequently asked questions, which has not been asked, but how to get super rich. Okay, to get super rich, you need to put somebody else in debt, right? Okay, so in other words, Victor? In the absence, yes. Yes.
Sorry, there's one other question, so I thought I should interrupt you just before you go on.
Yes.
Andrea Cavallari has a question, so I'll ask him to.
Okay, please go ahead.
Yes. Hi, Victor. Thanks very much for this great discussion. I have a question for you about the natural inequality business.
Yes.
So, in your world, if I am poor at one given point in time, will I stay poor all my life, or will I rotate to being rich? In
very good.
State of high entropy, because
yes. Yeah, very good, very interesting question, very good one. In some sense, to some degree, it's a question of kinetics, right? How fast we move, or how fast agents move. And to answer the question of kinetics, we actually need to know the dynamics. We need to know the actual equations of motion. The beauty of statistical physics is that the prediction of this exponential Boltzmann-Gibbs distribution actually does not depend on details of dynamics. So the beauty of statistical physics, you can predict equilibrium distribution actually without knowing the detailed dynamics of the system, as long as certain symmetries constraints are satisfied, like, for example, time reversal symmetry, okay? But to answer the question of kinetics, how fast things change, how long you stay there, etc., you need to actually know dynamics. And the problem is, we don't, I certainly, we don't really know what are actual dynamical equations in economics. We don't really know. But I can answer something about physics. There's famous question, molecules move around, right? In principle, over life of universe, very long time, every molecule is called ergodic hypothesis. Every molecule is supposed to sample all possible states. In the infinite life of a molecule, it should be sometimes rich, sometimes poor, etc. However, when people estimated the time it would take a molecule in the air to switch between being poor and rich, okay, the time is longer than age of universe. So that's what I read in textbooks. I didn't do the simulation myself. So basically, even in physics, even though molecules in principle ideally should sample everything, they actually do not, because it will take Colloquia longer than age of universe. So the point is, the distribution converges to this histogram pretty fast. But for any individual to sample all possible states, sure, it will take longer than lifetime. So one does basically one does not imply the other. Okay, I'm kind of running a little bit slow. I mean, so let me, because I do want to kind of do it in 40 or 45 minutes, whatever was the time allocation. You know what? Let me maybe switch to the second part of the talk, because many, I gave you kind of motivation. I kind of whet your appetite for this whole thing. But let me maybe switch to second part of the talk and show you the actual data. Because keep in mind, what I showed you so far is a purely hypothetical, very primitive, simulations. You may or may not believe it, and whatever. It may or may not be applicable. It's just a kind of introduction, motivation, whatever. And we can discuss it in a longer time. My understanding is after we finish the official time, after that, I will stay online, and anybody who want to ask questions, have discussion, they can stay online after the official end of the meeting. And I am willing to stay as long as you guys like, hours, whatever. So we can discuss it all in detail. But I want to finish the kind of the compulsory program. So let me switch to the next slide. Let me make, at this point, there is a little bit of logical disconnect. This is that, let me skip that because time is short. Okay, this is my second part of the talk. There's a little bit of logical disconnect, I must warn you. So after we published the first paper with the ideas that I outlined you in the first part, then we wanted to compare with the data. And the problem is it turned out very difficult to find data on money balances. I mean, it just, it principle, it exists somewhere, but it's very difficult to get. On the other hand, what is relatively easy to get is data on income distribution. Because people pay taxes, they report their income, etc. So this data is widely available publicly because there are statistical agencies that collect them, etc. So now, of course, income is different from money. Income is like flux of money. It's annual income. Moreover, it's annual influx of money. So of course, it's not the same thing. It's from physics point of view, to like power, energy per unit time. In any case, it's a different variable. So what I told you in the first part does not necessarily apply to the second part. But you know what? There is data on income distribution. Let's just do data analysis. That's, by the way, my second contribution is data analysis. So let's just download publicly available data and start asking question, what is this distribution? So the first exercise we did, we downloaded income distribution data from the United States Census Bureau. Data was from '96 because it was early, the first paper we wrote that. So anyway, the beauty of census is a survey data. People fill out questionnaires and report their income. So the beauty, it's a sample of population. It's not the whole population, but nevertheless, presumably good sample, whatever. So the beauty is we can download raw data and from the web, and then make a histogram. So we selected bins. Okay, so on the horizontal axis, we show annual income in the United States in the thousands of dollars. So these are kilo dollars. Okay, and we selected bins, whatever, by our choice, and we made a histogram. How many people have income in certain ranges of income? And so the gray kind of histogram is the actual data on income distribution from census. And the solid line is a fit to exponential function. So again, because there was certain inspiration, motivation, we said, why don't we try exponential function? And exponential fit actually works pretty well. Of course, we understand in physics that there is some deviation at the low end, but this is, keep in mind, this is below $5,000 a year. So this is very low income. And one would expect some problems near the boundary condition. It's like near the boundary. So there may be some deviations, whatever. But the way to see that it is exponential, as you know in physics, because if you expect exponential function, the best way is to take logarithm of it, right? If you take logarithm of exponential function, becomes linear. And that is what is shown in the inset. Now we plot probability in logarithmic scale, whereas income we plot in linear scale. And in these log linear coordinates, the data points collapse on the straight line. So you see there is a beautiful straight line. And this deviation at the low end doesn't even look so big in the logarithmic scale, because that is actually the relevant scale. So there is a basically beautiful agreement between the data on income distribution and exponential function. And nobody, statisticians, economists, they never heard about this. Nobody knew this. So we published our second paper titled Evidence for Exponential Distribution of Income in the United States. And since then, there were many follow-up papers. I'll show many more of those, okay? However, Yes, and of course the slope, the slope of this curve, we understand, is the inverse temperature, and the inverse temperature and the temperature is nothing but average, the mean income. So you can extract the average income from the slope of this curve. Okay, so far so good, but this data goes only up. There is some upper limit. It goes up to some level, in this case, $120,000, because this is done by survey of population. It does not sample very high income. So it does not sample super rich. It samples like middle, no. Okay, so we cannot really say what happens at the far end of the distribution. So, so we looked at a different data source, and that is IRS. This is Internal Revenue Service. This is American tax agency. And that is a huge data set, so about 100 million tax returns every year or something like this. And they have a small research agency called the Statistics of Income Research Division. They aggregate this data and they publish data, so the aggregated data is publicly available. However, they publish the way they publish. They publish at certain levels, like for example, $1 million, $500,000, $300,000, etc. They publish at certain discrete levels. They report it at certain discrete levels. And so for that reason, it's more practical to work with the cumulative probability distribution, which is simply the integral of probability density. The previous slide was probability density. What is in this slide is cumulative probability of the integral, but that's okay. Integral of exponential is exponential. Integral of power law is still power law. So what you see on the inset, and the inset is on the horizontal axis, we show again income, or they are called adjusted gross income in thousands of dollars. And the inset, the vertical scale is logarithmic and the horizontal scale is linear. And on this log linear scale, the data points again collapse on a straight line. That means that income distribution according to IRS data is exponential. And keep in mind, IRS is totally independent agency from Bureau of Census, and they collect data totally independently, but they produce the same result. However, what about super rich? And this is shown in the main panel. And the main panel is in log scale. Probability is logarithmic, but income scale is also logarithmic. And what we see is the upper part of the distribution actually falls on a straight line in log coordinates, which means power law. So basically, when you look at the whole distribution, what you see is from the point of view of data, you see evidence for a two-class distribution. Basically, the whole distribution, the main panel here, the blue points are data from statistical agency, and solid line, the black lines are fits. The whole distribution can be fitted very well as a combination of exponential distribution for the lower part, and that I associate with the name of Boltzmann, and the power law distribution for the upper part, which I associate with the name of Pareto. Okay, so remember those two portraits at the beginning, Boltzmann and Pareto, both were right. So the whole distribution actually has two parts, exponential and power law, the simplest mathematical functions, okay? And so this is my second contribution. I just made data fits of publicly available data. That's what physicists do. They measure data and they try to fit them with some reasonable functions, right? That's what I did. Data is publicly available. Anybody could have done it. But while power law was known in principle in economics, exponential was not known at all. And exponential covers actually majority of population. Because once you have these two fits, then you can take the intersection point as kind of operational boundary between the two classes. And for example, how many people are in the upper class? Well, you go here, right? And this logarithmic scale is 1, 2, 3%. So basically the upper class is about 3% of population, and the lower class is the remaining 97% of population. So basically the great majority of population, 90 whatever something percent, belongs to exponential, and a few percent in the top are different. They follow power law. So this is the 1% versus 99% that you probably heard about in the media, except that it's, well, not exactly 1%, maybe 3% or something. And it is in the data. It's a kind of, it comes from objective fit of the data, if you like. Okay, and on that subject, and this by the way known in physics, some branches of physics like plasma physics, astrophysics, space science, whatever. The lower part is called thermal because it's exponential, and the upper power law part is called superthermal. And we have Goddard Space Flight Center who has satellites and they measure cosmic, whatever, solar wind, whatever. In many branches of physics, there is a kind of similar distribution, cosmic rays, whatever. Okay, but in interesting other observation, I want to emphasize that there is no, according to this data, there is no such thing as middle class. According to this data feed, there is upper class and lower class, but there's no middle class in terms of data definition. Because if you look at the data from $100,000 per year to zero, the distribution is completely smooth. It's just a straight line, logarithmic scale. So if you want to define middle class, tell me, where to put the boundary, where to put the cutoff. I don't see any natural breakpoint in the data. And by the way, when you read about middle class in the newspapers, there is no commonly accepted definition of middle class. Anybody who writes about middle class, they make up their own definition of middle class. So there's no consistency whatsoever. Anyway, so this was one particular year. But what about, maybe that was a special year. So after that, we analyzed about 30 years of data. Of course, during this time, things change. In particular, the average income changes. There is inflation. In 30 years, the nominal income increased by United States, increased by a factor of 2.5. So basically, we need to normalize for this. So for each year, we download data from IRS. We do this exercise. We get this log linear straight line fit. From the slope of this, we extract income temperature, the average income of the lower class, and then we normalize to this average income. And that's what we get. So this is a similar graph, but now income is normal, rescaled income. We normalize income to average income in that year. And what you see after that, the data points basically collapse. So this inset is in log linear scale, and you see basically data points. This, of course, there's many, many years. This is 30 years of data here. Okay, so superimposed by different colors and symbols. Basically, data points collapse on a straight line for the lower end, and we just separated these years and these years, but basically it's still exponential both ways. The main panel again shows the exponential part, and it is extremely stable, and then the power law part. So again, I just separated two sets of years, but it's basically the same thing. So what we see is this exponential distribution for the lower class, which is majority of population, is extremely stable. So 30 years pass by, relative inequality within lower class does not change. The scale changes. Yes, the average income increases, but normalized in relative sense, there's no change of inequality within lower class. That's presumably, that's my guess now, my speculation, because it's state of maximal entropy is like thermal baths. On the other hand, there is significant change of the upper class. Upper class does go up and down. I show you the next slide. The upper class is highly dynamical. And in fact, I will argue that it is dynamics of the upper class versus lower class that actually captures all the dynamics of income inequality. So let me now show next slide, kind of time evolution of this data. See, once we have done this kind of decomposition into two classes, then we can extract a few parameters that characterize this whole distribution, and then graph them as a function of time from this, from more than 30 years of data, from early 80s to late 2000s. Okay, so there are very, very busy graph. I will probably not explain every single graph, but let me focus on this red curve. Okay, so this red curve shows the fraction of income that goes to the upper class. You see, because we can decompose distribution into two parts, we can ask, I told you that upper class is a few percent of population, but another question you can ask, what is the fraction of income that goes to the upper class? And that fraction is significant. And it can be actually very easily calculated by this formula. You can simply take the average income in the whole population ensemble. This is the black one, okay? And take the difference with temperature. Temperature is the average income of the lower class. This is the blue line. Okay, and the difference is what goes to the upper class. And this is the red curve. So what you see is that between, say, 85 and 95, it was at the level of about 10%. Okay, whatever. But then from about 95, it started to increase very rapidly. So share of income of the upper class in the late 90s started to increase very fast. And what was happening in the late 90s, you may or may not remember, it was dot-com bubble. There was a bubble in the stock market. And during the bubble in stock market, a lot of money were flowing to upper class. And keep in mind, this is not just a stock market index. This is actual income reported to tax agency. Okay, but then of course it was a bubble, so bubble crashed, and the share of upper class shrunk. There was a collapse, whatever. But then next bubble started, real estate bubble, housing bubble, because prices of houses never go down. Stocks are risky, but real estate is forever. Well, so again, so that bubble started, and share of income of the upper class increased again, exceeded 20%. But that was a bubble, it crashed. Okay, so the share of wealth shrunk again. And now we see another increase. What is this increase? What is this due to? I don't know, but my hypothesis, I call it quantitative easing bubble. That's because of bailouts that we started 10 years ago. Central bank starts to print money and inject them into the system. And central bank does have authority to print money. So speaking about conservation of money, ordinary people like you and me, we can only get money and give money. We cannot grow money on money trees. But central bank because of its territory, can actually inject money. So this is like external source. And that's basically what they did. And so they injected huge amount. That the balance sheet of Federal Reserve was below $1 trillion, and then it increased to more like $4 trillion during this period of time. They quadrupled balance sheet and injected this money. Now they injected even more, of course, because of the virus. And because banks, okay, so anyway, this, because the central bank can only deal with banks, effectively this money were given to banks, that mean to bankers, and bankers said, great, great, give us even more. So basically my argument is that the third increase of inequality is actually due to monetary policy of the central bank specifically. But anyway, this is of course maybe controversial kind of hypothesis. Okay, I'm kind of running out of time. You know what, there are more things to discuss for this graph. If you ask me a question, I show more, but let me try to get kind of to the end. I do want to show UK data. Okay, so yeah, in fact, I have about 2 slides left. So this is data for the United States. What about other countries in the world? Now I'm getting to UK data. And so in this relatively recent paper published in 2019, we actually look at the data from many countries, like 67 countries around the world. This was done in collaboration with the Chinese collaborator, specifically Yong Tao. So he's originally a physicist by education. Now he's professor of economics. And so he speaks both languages, and I don't mean Chinese and English, I mean physics and economics. So this is like one quote from the abstract, and the first part of it, if you read it, I maybe don't want to read. First part is like economics, Arrow-Debreu model, Rawls fairness principle. Rawls is a philosopher. Well, produces exponential distribution. That's basically by maximization of entropy, and it agrees with the data for 67 countries in the world. So I only have 2 slides. At this slide, I show you data for the UK. And next slide shows you the data for those 67 countries in the world. Okay, so this data comes from UK National Statistics, Her Majesty Revenue and Customs. Okay, okay, yeah, I get the message. Yeah, I will stay for another hour, afterwards to show you more. Okay, so data comes from Her Majesty Revenue and Customs, statistic survey of population. Okay, Gini coefficient, I will explain. Gini coefficient is a technical question. I'll explain a little bit later, maybe after the main part. So anyway, we download the data, and these are for many years from the UK Statistical Agency. And this is the raw data. That's raw data as published. Okay, and what you see, and it's plotted in log linear scale. The vertical scale is logarithmic. The linear scale is linear, and it is normalized. Again, income X, now X is income. Is normalized to the average income in each year, and what you see, the points basically collapse on the straight lines. However, of course you see deviations because there is a tail. There is upper class, there is power law, whatever it is, tail. Okay, the first question before tax. My data is usually before tax. So data mostly before tax because I want to apply kind of statistical physics. Tax policy is not statistical physics, some deliberate action. So the data analyzes before tax because tax policy is modification due to policies. And that's interesting, another interesting question, but it's not so much question for statistical physics, what should be a tax policy. Anyway, data mostly pre-tax. Anyway, so there is deviation here at the high end because of the upper tail. But to observe exponential the best, what we did then, we did a little bit of processing of the data. We said, let us remove a few points at the top because we plot cumulative distribution functions. So it's an integral. We start integrating from the top, and the top is not exponential. So it kind of distorts the result a little bit. So we just truncate it. We just remove the couple % of data points at the very high end. And so we produce truncated CDF. And this truncated, after you remove the high end, is perfect exponential, a beautiful exponential agreement for many years. Let's put it this way. In my experience, I work in condensed matter physics. And I can tell you, in condensed matter physics, in my experience, organic superconductors or whatever, you name it, it's very uncommon. It happens, but not very often, to see such a good agreement between data and the theoretical function. Usually in condensed matter, we accept much worse kind of level of agreement as the proof of whatever statements we try to make. And there it's really beautiful. So this is data for the UK. And finally, that's pretty much last slide. So this is those 67 countries of the world. And I group them into 2 groups. One is the European Union countries and other countries in the world. And all of this data plotted in log linear scale. The income is rescaled because different countries have different units of money. But we see, but I don't want to go, you know, country by country basically, but you can see this like overwhelming evidence of exponential distribution. Just one example, look for China. You know, that's maybe special. For China, this exponential distribution stretches very far, up to about maybe 5 times the average income. Okay, however, I need to say a few caveats here. What is shown in this graph, again, it's not the whole data set for each country. Remember, the upper part is not exponential. It follows, say, power law, whatever it is. So we truncated upper parts in a similar manner as we did for the UK. We removed upper part with some few percent at the top where distributions is, you know, not exponential, the power law, whatever. Okay. And also another thing is the lower end of the distribution, maybe not exponential, because, you know, countries have social policies, welfare, etc. And so you mentioned tax, you know, whatever. There are policies for tax, for income redistribution, subsidies, whatever, and they may reduce population at the low end. So in other words, exponential does not necessarily extend all the way to zero. United States is maybe a special case because maybe of the lack of social policies. It extends almost all the way to zero. But European countries, many of them have quite strong welfare policies. So the population at the low end is reduced because of social policy. So exponential does not go all the way to zero. So in other words, the message here is exponential distribution. I think it's Norway. This is Norway, right? So Norway, as you would imagine, there is probably social policy at the low end to reduce it. And on the other hand, exponential goes all the way up to 6 or 7 times the average income. It extends very, very far to relatively high income compared maybe to some other countries. So the middle part of the distribution, not too low and not too high, is exponential. And that seems to be the universal feature. And of course, maybe my last words on this is that, you know, physicists, there is some certain, how should I say, a little bit of philosophical, I should say, discourse, you know, not to say antagonism, but something along those lines, between, say, physicists and maybe social scientists, economists specifically. In physics, we really look for universality, okay? Let me answer this comment. In physics, we look for universality, we look for universal features. That's what we like a lot. But of course, there are variations. Every material, I work in material science, every material is different. So we don't study materials one by one. But at the same time, there are universal features which are common for, you know, same in economics and whatever. So what was identified here, certain common universal feature of inequality. But of course, there are differences between countries. You know, one can do country by country study and observe different, different specifics. Okay, so I think I pretty much. Just a second. I think I pretty much finished. No, sorry. At this point. I have twice more slides, just to let you know, but my time is basically up. So I show you conclusions. And just very briefly, I told you about exponential distribution of money if you have boundary condition. If you have debt, it may be not necessarily stable. You need some limit on debt, okay? And income distribution has a 2-class structure. The lower part is exponential, very stable. The upper part is power law and not universal in the sense there is a high dynamics. And what I didn't have time to discuss is global inequality among countries of the world as measured by energy consumption and carbon emissions. Okay, that's another side of the slides. Okay, so so I think I'm pretty much done. And okay, so I think I should probably stop now, show the last official slide. And there are quite many questions on the chat, and the questions were also asked by voice. And, you know, my plan for the next hour or more is to stay online. I'm sorry, I should not know this. For next hour or more, just stay online and answer those questions. So what you have seen is more like trailer, like preview to whet your appetite, but there is a lot more to discuss. So thank you very much for your attention, and I'll take many more questions.
Thank you, Victor, for a great talk. So I think at this point, we will stop recording, but we will stay here. So because then we don't have a bandwidth barrier, people can actually turn their videos back on. And I think we can try and have a free-flowing discussion. but I think it's good if people stay muted unless they're asking a question, and I'll try and moderate it. So please, you don't have to ask your question in text, but just stick in a message in the chat to everyone saying you'd like to ask a question.
Yeah, so maybe I'll answer questions. Maybe I'll first answer questions which are on chat already.